All right, I'm gonna click back over to my class real quick. If you're a tablet user and you like doing that, we have what I'm working on right now is, and I have the PDF and Word document for it. I'm working on these notes right here. Okay. So if you'd like it, you can download it and write directly on it and like save yourself some writing. I recommend you write some stuff. I am going to switch over to the document camera quite a bit because I think it's easier to write bigger with big pens. We're going to start with 1.1. The first page, we're going to talk about like the big picture of calculus. So this is like an intuitive approach of limits. Let's say we have some function f and a point on the function f, x naught, y naught, and we want to find an equation of the line that is tangent to that graph. And so we have an example here. We're going to use y equals x cubed. We're going to use the point 1, 1. And I got that written over here. So, wow, I need a little bit brighter. Motherfucker. There we go. Okay. So does anyone remember what a tangent line is at a point? It's a trigonometry. It's in trigonometry idea. But in trigonometry, we tend to use tangent for something different. If you don't, here's an example. I'm not going to draw y equals x cubed because it's a little harder to draw a tangent line with y equals x cubed simply because of the shape of the graph. But like, let's say I've got some curve like this. This is my function f. And I've got some point P right here at x naught, y naught. Or let's say this is 1, 1. The tangent line only hits the graph at one point. That's my tangent line. Tangent line to f of x at P. Well, we want to find the tangent line. One of the forms of way of writing a line, a line is y equals mx plus b, right? I need m and b. We'll start with m. What do you need to find m, the slope? Does it take you back to algebra? Rise over run, right? y2 minus y1 over x2 minus x1. We need 2 points to find a slope, and I've only got one. And I could say, well, there's a point there, but I don't know what the value is. So what we do is we'll pick a different point somewhere else on the graph. We'll call that Q. And now we've got 2 points like that. And I don't know what that coordinate is. That's an x, y. Those are variables, x, y. X naught, y naught are substitutes for values. X, y are clearly variables. This is the secant line. A secant line crosses at 2 points. Tangent line crosses at 1. So the idea here is use green. I haven't used green very much except the main line. As Q gets closer to P, the slope of the secant line gets closer to the slope of the tangent. M tangent. So like pictorially, let's call that Q0. Q1 is here, and it's like that. Q2 is like that. I could get one really close, call that Q3. And now we've got that for Q3. And eventually, as Q gets closer to P, you'll see that this tangent line is starting, it's slowly rotating, and eventually it's going to line, or the secant line is eventually going to rotate with the tangent line, right? This is kind of like the idea of the limit. As we don't need to say as Q is approaching P, this is really as X approaches X naught. I can narrow it down to that. Because this is on a graph as X, this is the X value. Really, the X value is getting closer to X naught. So we don't need to focus on the point. We'll just pick a variable and go with it. We can go with Y, but like we intuitively do a lot with the X, yeah.
So can the X value ever be equal to X naught?
Yes. On graph, like in this graph, yes, X can equal X naught. In fact, we're going to take advantage of that in a second. Yeah.
Maybe a stupid question, but what is X naught?
So like in the example equation right here, it's the 0.11. X naught, Y naught is, it just stands for two unknown or two quantities that we haven't given yet. So whatever, like if I had said it was 0.23, X naught would be 2 and Y naught would be 3. All good questions. Does that make sense to everybody? Okay, I'm gonna try to shift into how, oh wait, people are so white. Let me just pause and let everybody get caught up. Like this is like, if you can grasp fully what we're doing here or why we're doing it is a better thing. Why we're doing it, like the limits are going to make a lot of sense. Limits will make a shitload of sense. And then derivatives, when we get to chapter, is it in 2 or is it in 1? We might even hit derivatives in 1, but I think it's chapter 2. Derivatives will make sense because we build derivatives off of limits. I actually have our example y equals x cubed in Desmos, but I'm not going to show the tangent lines yet, or the tangent line and secant lines that I had plotted yet, because it's like y equals x cubed is a shitty graph to do it on. Imagine trying to draw a tangent line easily on x cubed. You know how the fucking graph is. Give it a little bit longer. Pins are still going. I love Justin's last name. Justin's last name is Vander Meiden. I think I'm pronouncing it right. It totally looks like some elitist, like someone that would be friends with Paris Hilton or some shit like that. You're going to COS, so you're probably not a rich snob. It's got that Vander Meiden name. Just rings snob to me. Okay, cool. I am saying it right. You're not a rich snob, are you, Justin? Too good to show up to class. That's why you're on Zoom. He doesn't think so. Okay, good. I didn't think so. Generally, rich snobs don't go to community college. They're like, I'm too good for that. Which is stupid. Community college teachers tend to be better than university teachers. Which surprises the shit out of a lot of people, but it's true. Because all we do is teach. That's what we chose community college because that's our job, teaching. At a university, their job is doing research. Teaching is like answering emails for them. It's something they have to do as part of their work. So some of them are good at it, some of them are not. And that's true at community college, but there's more of a There's a wide range of teachers at university level. All right. So I'm gonna put that to the side. We're gonna switch over and look at our example, do that one by hand. So to get that equation or get the y equals, we want y equal, I'm off the screen. To get y equals mx plus b, we need m, and we can figure out b. And we said m was y2 minus y1 over x2 minus x1. I've got the points P is x naught, y naught, which is 1, 1 for our problem. That's the shadow. There we go. My hand doesn't have a shadow for there. And then we'll use Q is x, y. Well, I'll make this point 2. And I'll make that point 1. And so this turns into m equals y2, which is y, minus y1, which is 1, over x2, which is x, minus x1, which is the x naught, which is 1. And recall, we're working with the line y equals x cubed. So this is what we can do. This is the secant line, remember? Okay, so secant line right here. Secant line has 2 points. I know everywhere on the graph, y equals x cubed, y actually equals x cubed. I'm going to substitute that shit in. M is now x cubed minus 1 over x minus 1. Anyone have an idea with what I can do with it here?
Take x1 out.
Say that again?
You can take x1 off with x minus 1 off the bottom because x
I can't cross them out of there are, but I can factor and cross off. Anyone remember how to factor x cubed minus 1? It's probably been a while, even if you went straight from pre-calc A to pre-calc B to here, it's probably been a while. A cubed minus B cubed is A minus B times A squared plus AB plus B squared. So if I do that here, A is X and B is 1. I've got X minus 1 over X squared plus AB is 1 times X plus B squared is 1. So that's the top factored. And the bottom is X minus 1. And that's my secant line still. So we can see this equals X squared plus X plus 1. That's the slope of the secant line. Well, that's weird. It doesn't have any, it's not a number, right? Slopes are numbers, right? We shouldn't have a variable in slope. What can we do about that? Remember, we're trying to find the slope at 1, 1. And we said as the secant line, as x approaches x naught, the slope of the secant line approaches the tangent line. We could look at doing like x equals 1.2, x equals 1.1, x equals 1.01. In this case, x equals 1 is not a problem anymore. X equals 1 is okay in this one. So I'm going to just plug it in. But I am going to show you the values of the other ones. If I do 1 plus or 1.2 squared plus 1.2 plus 1. Let's see what that value is real quick. Oh. So this value here is, maybe I'll change colors. It's got all blue. This is 3.64. And if I do this one, 1.1 squared plus 1.1 plus 1. I've got 3.31. If I do this one right here, 1.01. Oh, let's do this. 1.01 squared plus 1.01 plus 1. What do I get? .031. 0301, sorry. And if I do this one, x equals 1, I got 1 squared plus 1 plus 1 is 3. The way I drew the picture, we had Q on the right. But Q doesn't have to be on the right. We could have done Q on the left. If we had done like 0.8, 0.9, 0.99. Let's see what those values are real quick. 0.8 squared plus 0.8 plus 1. 2.44. 0.9 squared plus 0.9 plus 1. 2.71. Off screen. .9701. So let me give you guys a chance to finish writing that down if you're going to write it down. This is why I didn't try to do this, show the secant line graphically here. Because even if I said like 1.2 is here. 1.2 had a Y value of 3.6, or M is 3.64. I'm off screen. There we go. And if I said, but that's trying to draw that as a secant line. And that's really hard to see. So I thought it was easier to do the other one. But we saw M was 3.64 when we had this line right here. M was getting a little closer to 3. This was like maybe, let's say this is the 3.31 for 1.1. When we were coming from the left, say 0.8 is right there. 0.8 is like that. That was our 2.44. And we can see that, like, no matter which way we go, the slope is going to get to that tangent line, which is really hard to draw now that I drew a bunch of other shit there. Going right there. That's our tangent line. And we can see 2.4 coming from the left, 2.44, 2.71, 2.9701. These values approach 3. That was coming from the left. This is a lot of computation shit right here, but there's a point to it. You'll see it in a second. Coming from the right, we had 3.64. .31, 3.0301 as we got closer to X. This is also approaching 3. So even if I don't plug in X equals 1, let's say I didn't plug that part in, cover that up. Like, let's say I couldn't, let's say there's a hole in the graph there. I could still figure out what the tangent line would look like there just by looking at the secant lines as it gets closer. Does that make sense? So this would work even if I had a hole there. I could still do the same thing here. I can get a tangent line there even without a point there if I just look at the secant lines as it approaches it. I don't have the line yet though, do I? I just have the slope. We had m equals y2 minus y1. Or if you multiply through by x2 minus x1, you get y2 minus y1 equals m times x2 minus x1. And now we have values for all of these. For the way we set it up, this was y minus 1, and x2 minus x1 was x minus 1. And now m of the tangent line is 3. We can see it's 3 coming from either way. And we clean this up. I've got y minus 1 equals 3x minus 3. So y equals 3x minus 2. So we just found a line that was tangent to y equals x cubed at just a single point without having any other point on the line. I could find another point if I plug in x equals 2. Y equals 3 times 2 minus 2. 6 minus 2 is 4. So there's going to be a 0.24 on the tangent line. Notice it's not on y equals x cubed. 2 cubed is 8. Would be that one. Yeah.
So would -2 be the b value?
Yes. -2 is the b value, which is our y-intercept. I did this. Yeah. Go ahead.
What'd you do to the slope to get the like full equation? Because I see you got the variables and then you get them side by side on either end of the equation.
Here,
Yeah,
I multiplied both sides by x2 minus x1. And then I switched sides. I took this side and I put it over here. This side, the denominator crosses off, so we just have that.
So is that a generic way to just find the whole equation?
Yes, in fact, this right here is called the point slope form of the equation. Point slope form. And y equals mx plus b is called the slope intercept form. And theoretically, your teacher in algebra talked about both of those forms, but granted, it's been at least a year. Well, approximately a year. If you took it in last fall, you probably didn't do like the lines until like September. That's 11 months still. You're right, Sensi? Look hungover. Looks like. Carla, Justin, Michael, you guys good?
Yes.
Awesome. I really shouldn't have started writing all over the page. Going back and forth, because I'm like, I know people are looking at it going, okay, what do I gotta fill in here? If I just pulled another page out, it would have stayed in fucking order. Sorry about that. Well, people are still writing, so I'm waiting patiently. All right, let's take a look at this on Desmos. I have the graph of y equals x cubed right here, and I've got, let's label it real quick. Really? No mouse wheel? Look at this shit. Oh, well, I guess we're not doing mouse wheel. So like if I did y equals x, that's going through 0, 0 right here. And 1, 1. And we can see the slope there is 1. It's the coefficient or number in front of x. If I do another line, this is going through 1/2. X equals 1/2 or 0.5. The slope is getting larger. And the point x is getting closer to x equals 1. And when we look at y equals 3x minus 2, let me turn off the other two. We can see it actually does only touch the line once. In this case, we were able to plug in x equals 1 directly and find it. I do want to point out real quick. What would have happened if we had plugged in x equals 1 right here? I get 1 minus 1 over 1 minus 1, 0 over 0. That tells shit, right? How does 0 over 0 equal 3? That's fucking crazy, right? But we're going to be doing shit like that this semester. Sometimes the denominator is 0, but we can find what happens as we're approaching it by factoring and canceling some stuff out. And so where x equals 1 doesn't work here, x equals 1 works just fine here. So sometimes we can still do it. That's the idea of limits. We're going to delve into limits more in a second. That is going to lead to derivatives or differential calculus, which is going to be like the first half of our class, first half of the semester. The second half of the semester is doing integration calculus or integral calculus. And if I go back to our notes here, if you're using a tablet at home, you can see it down here. Let's say we have a function f, and we want to find the area between the graph of f and an interval AB on the x-axis. I'll give you guys a second to write down this problem. I'll sketch it in general in a second on the paper. What is that bracket A, comma, bracket B, or bracket A, comma, B, bracket mean? This is from algebra also. Yeah,
Means the values for the line are included.
the brackets mean, yeah, the A, or the values at the end are included. The A, comma, B means everything in between. So this is actually an A, X value, or X equals A and X equals B value. Michael, I will be uploading the lecture notes. So I wrote down the question over here and I drew a picture real quick. Well, I wrote down part of the question. We'll do the approximating in the Desmos because it's a pain in the ass to do by hand, just takes too long. So if I have, this is my x-axis, obviously, and my y-axis. And this is my y equals f of x. I've got some point here where x equals a, and another point here where x equals b. And it says find the area between the graph of f, which is this line right here, and the area or the line a, x equals a to x equals b on the x-axis. So my other line that I'm looking at right here is this one, my x-axis. And we want to find that area right there. So that's what we're looking for. That's pictorially what this means. All right, back to Desmos, just look at the problem we have here. We have y equals 1 minus x squared, and we're going to do 0 to 1. So if you're at home and you're using a tally, you can actually just click right on this, and it'll take you to this. So the way we do it is we like break it up into rectangles. Here I've got 10 rectangles, and like the left corner of each rectangle is actually touching y equals 1 minus x squared. Can you guys see that? Does that make sense? I've got a rectangle right, it might be easier if you see less rectangles. I've got one big rectangle right here where I'm touching at 0, 0, and the right endpoint is 0.225. And then I got another one right here, 0.225 to 0.45. And I could do this and I can break it up into smaller rectangles. Looks like the area is getting worse, right? I've got a lot of extra shit here. What I'm looking for is if I go all the way up, which looks pretty close, I'm looking for this region right here Let's see if I can zoom in though. You dirty bastard. There, now I can zoom in. I just gotta go slow. If I zoom in closer, I can still see there's a little bit extra. So even when I do rectangles, there's still a little bit extra. And the less rectangles we have, the more extra we have. That's when we have our rectangles touching the line on the left side. If I do touching the line on the right side, now I'm missing some of that. I'm missing this white region right here. And the less ends we have, the more white region I've got. Like if I go down to n equals 1, I've got nothing. N equals 2, I'm missing a shitload. N equals 10, not too bad. Still off. As n gets larger, we can still see, if you look closer, still a little like, it's a little step ladder, and there's still a little bit of white spot there. So that's not quite, even breaking it up into these rectangles and finding the area of the rectangles. If we have a specific number of rectangles, it's not going to work. We get close. Let me go back down to something where you can see a little bit better. We can also do it where we're at the midpoint. So for each of my rectangles here, let me go to smaller rectangles. I've got a rectangle right here. The first rectangle, the midpoint is touching right there. So we're picking the height so that the midpoint of X is right there in the middle. Here we've got a little extra on the right, but we're missing some on the left. And that happens on each of them. For this rectangle right here, the second rectangle, I got a little extra right here, but I'm missing some right here. And it's saying it keeps happening that way. If I add more rectangles, the area of the two kind of offset each other. We're going to be doing more with this by hand a little bit. This is doing the summation of the area of those rectangles. So like, let's look at it from the left side. For 10 rectangles, that's saying the area is 0.715. If I go to fewer rectangles, it's getting a little higher, 0.76. If I go to higher rectangles, I'm getting down to 0.67165. That's doing the right-hand side or the left-hand side. If we go to the right-hand side, let's see what happens as we do more rectangles. When we had n equals 10, it was 0.615. Here we're going upwards. I'm actually going to write this down. N equals 100 from the left is 0.66165. And from the right, it was 0.67165. If I bump this up to n equals 10,000, you can't see 10,000 rectangles. So I'm just going to show you the results that we get. The left-hand side says 0.666716665. The right-hand side says 0.666616665. And what's the midpoint one show? It's got a shitload of sixes. This is making more and more rectangles that are narrower and narrower. Does that make sense? What happens if I use an infinite number of rectangles? Well, I can't really use an infinite number, but what if we say n approaches infinity? As n gets larger and larger and larger, let's say it's 10 billion. These values converge. And it looks like it's going to 0.66 or 2/3. It looks like the area is going to become 2/3. This is doing stuff with integrals. We are going to do this in the second half of the semester. Sometimes finding that area is very, very, very important. Like if you're looking at the amount of pressure in an area, how much pressure is being caused in a certain region, we can add it up like this. But like trying to do rectangles, the only real way of doing this, we could do this physically. I could get a metal plate and cut it to the perfect dimensions and then cut out like a 1x1 square so I know what a 1x1 weighs. And then I could figure out how much all of it weighs and multiply it. We could find it by doing like a physical application, but the easiest way is doing integration. And we were going to do that the second half of the semester. That's the entire concept of what we're doing this year. Okay. I'm gonna make it so you can see what we're writing next. We haven't actually used limits yet. I've just been doing big, like the idea of limits rather than doing limits. We will write LIM for limit. And we put X arrow A underneath it. X arrow A means X approaches A. And so if we're looking at the limit as X approaches A of that f of X, this is like when we did the y equals x cubed. We're going to get some value, L. L here is just a value. We have X approach A, but notice it says not equal to A. And some points, just like we had with our secant line, we couldn't plug in X equals 1 initially. So we're going to take values close to A, but not equal to A. We're going to use numerical evidence to make a conjecture about the value of the limit x equal x minus 2 over x squared minus 4 as x approaches 2. I'm going to write this down on the document camera, and we're going to work with it up here. And we want to figure out what that equals. This is like saying y equals. Oh, let me come over here and do this. graphically, this is what we're doing. Desmos doesn't show it very well unless I actually click on the button. We're trying to find the value of y. When, or what y would equal if we could plug in x equals 2. This is the equation we're talking about right here. If I actually plug in 2, Desmos says it's undefined because there's no value there. 2 makes a hole in the denominator and it breaks this equation. So what we're doing is we're going to go, what happens, what value are we approaching as we come from the left? As I get closer and closer to 2, what's happening with y? It's slowly going down. It went down below 0.3. It went down, it's below 0.26 now. It looks like it's getting pretty close to 0.25. As soon as I get to 2, it's gone. If I come from the other direction, the closer I get, it looks like it's approaching 0.25. I've got 0.247 when x equals 2.05. As I get to 2.01, I'm at 0.249. And then if I did 1.99, it was, that's hard to move just a hair. 1.98 is 0.251. It looks like between those two is 0.25 exactly. We're going to do that by hand. That or conceptually what's happening here. So we can't plug in x equals 2. It breaks the denominator. Breaks the bottom. So let's just do a couple values approaching from the left and from the right. 2, this is our mystery value that we're trying to tackle. We'll do 1.99, maybe 1.95, and 1.9. And the other way, 2.01, 2.05, and 2.1. And we can do this in a calculator. 1.9, oops, minus 2 divided by parentheses 1.9 squared minus 4. This top one is 0.2564. I do it again with the next one. I get 0.253. We'll just do, man, I got right. The hell? Oh, I hit the button. There we go. I'll do 0.99. This is 0.01 divided by, no, that's not, it's negative 0.01. Divided by parentheses 1.99 squared minus 4. I get 0.2506. And we'll go the other way. I want to cheat and use Desmos because it makes it go a little bit faster. .1 is 0.244. .247. And we had 0.251. I remember that. I'll write down over here what I did. I was doing in the calculator. What I did was y equals 1.9 minus 2 over 1.9 squared minus 4. I was plugging in my x value into that. Yeah,
Where did we get y equals x minus 2 over squared minus 4? Where did that come from?
just from the example problem we gave. This is what when we're doing, we're finding what y equals. What the idea of doing limits is, the reason why we do limits is when we want to find a value that doesn't actually exist. What would it be if it did exist? The guy had his hands up first, then we'll go with you. Did I do the wrong fucking value? You might be right. Good call. I told you I was gonna fuck some shit up. I can't even use Desmos right. Amateur. And the reason why is when we're graphing a line, the better question about why am I using this thing right here? We normally say y equals f of x. That's my y right there. So I'm doing an x and y thing right here. Since f of x is y, I just replace it with y. I could put f of x here, which might be a little easier to understand. X equals 2 does not exist. DNE is short for does not exist. God damn it. But it looks like the limit L is 0.25. Notice we can do a little more with it, and we're going to do this in 1.2 in the latter half more. But if I do that factoring idea, x squared minus 4 is the difference of squares. A squared minus b squared is a minus b, a plus b. So x squared minus 4 is x minus 2, x plus 2. And if I cancel shit out that's on the top and the bottom, this becomes the limit as x approaches 2 of 1 over x plus 2. So if your factoring skills are rusty, you're going to be using a lot of 1.2. So brush up on them. Meet with me on Zoom tomorrow morning. Come over to the Mesa Center over in Visalia at any time, but I will be there from 2 to 3. And we can work up on it. Notice that I can plug in 2 here. If I do x equals 2 here, this is 1 over 2 plus 2, which is 1/4. And that's our 0.25, right? So if we can make it so the value that we're trying to approach, if we tinker with the equation, in this case by factoring and canceling, we can plug it into a later form, we can find the limit that way. X equals 2 is called a discontinuity here. the line is not continuous at 2, there's a hole there. So we saw on the graph. There's an asymptote right here at -2. And we're gonna put 2 there. As it comes down, Desmos doesn't show the hole very well, but I can show the hole well here. This is y equals x minus 2 over x squared minus 4. And we can see that even though y is undefined at x equals 2, we can find out what value it gets close to. If it wasn't undefined, it would be would be 1/4. That's what our limit shit found. The next one we're going to look at, we're going to do Desmos because doing the calculator thing is really slow. We're going to look at this idea on Desmos. We're going to have y equals sine x over x. And so that's really my f of x. And we're going to do the limit as x approaches 0 of f of x and find out what does that equal. Or the limit as x approaches 0 of sine of x over x. Now I cannot plug in x equals 0, right? This breaks our function. You guys write it down, we'll look at it pictorially. Desmos is kind of nice because like, even though we don't see the hole at x equals 0, if I click on it, I can show it. But pictorially, looking at it graphically, we can see right away what that value should be if it existed. All right, let's go take a look at it. This equals y equals sine x over x. Remember, sine x is that wave. When you took it in trigonometry, it's a wave. Adding in the dividing by x, notice it's getting flatter and flatter as it gets away from 0. Like the further right I go, this gets really flat, but it's still oscillating some. It's still going up and down. We want to see what happens at actually x equals 0. As we approach it from the left, values start below 1 and they go up to 0, or they go up to 1. 0.99 gets pretty fucking close. Wow, even at negative 0.03, it's rounding up to 1. It's already got so many 9s. And if I come from the right, it's doing the same thing. 0.99. And as we get close to x equals 0, the value of y is 1, but it doesn't actually equal 1. So we did this on Desmos. we showed that the limit as x approaches 0, sine x over x equals 1. I want to point out, I've been coming at it from both sides, looking as it approaches it from both sides. That's the big picture of limits. But we can do one-sided limits. We can approach it from just the right. And if we would don't want to just approach that value from the right, like if we say x approaches a from the right, we're going to say, we're going to put a plus. It looks like an exponent. X approaches a from the positive side, or x approaches a from the right. And if we want to approach it from the left, or values that are less than the number, we say x approaches a from the minus side, or x approaches a from the left. These are both one-sided limits. And we'll take a look at them in a second. These one-sided limits are important because they need to equal the same value for the actual overall limit to exist. And I'll show this on the next page. People are still writing. But for those of you that aren't writing, that's where we're headed. If they approach different values, as you'll see in one of our examples, if they approach different values, the limit doesn't exist. Almost ready for the next page. I see pins still moving, but everyone should be getting pretty close. All right, so. Let's give you, let's zoom out just a hair. So we want to show that for the relationship between the one side and the two-sided limits, we need, what this paragraph says is that the limit as we approach from the left has to equal the same value as it approaches from the right for the limit to exist. F of X has a limit as X approaches C. If and only if, this is some great math jargon. If and only if, when you start doing proofs, and we're not doing it in here, but if you're an actual math major and you don't go into an applied math degree, you'll go into a course like real analysis and stuff, and you do a lot of proofs, and if and only if means that the statement on the left can lead to the statement on the right, and the statement on the right can lead to the statement on, if you start with the right, it leads to the left. If and only if, that's for another day. The point is that the limit as X approaches C exists only if the limit is the same value as we approach from the left, C minus. And as we approach from the right, C plus. They both have to equal L. So if you're going to sketch this graph in your notes, the important values to sketch, you want to have the graph, or at least the point in the right spot at 1, at 3, and part E has a 0. So make sure you've got your 1 looks like this value right here, your 3 looks like what it should look like right here, and 0 looks like over here. Other than that, this graph doesn't need to go exactly up to 3. You can make it some wavy thing in between these two. As long as you're connecting these dots correctly in a straight line there, that's fine. The wavy parts, you don't have to be precise with the wavy part. As long as your starting point and your end point are the same, are correct. And we'll take a look at doing one-sided limits here. Believe it or not, we're going to get 1.2 done today. 1.2 is a lot easier. 1.2 is going to be a lot of just plugging shit in. This is just making sure you understand the idea of limits. Actually computing limits in real time, normal stuff is fairly easy. You can do it on Desmos. If you can actually plug the value in, you just plug it in. As we will see in part 2 or 1.2. So if we're looking at the limit as x approaches 1 from the plus side, x equals 1 is right here. As it approaches 1 from the right side, this value is getting closer and closer to y equals 0. So for that graph, the limit as x approaches 1 from the right side is 0. And if we look at it as it is approaching from the left side, we follow this squiggly path here. Ooh, as we're getting closer and closer and closer to x equals 1, it looks like y is approaching 2. So for this, we're going to say the limit as x approaches 1, part C of f of x, it does not exist. I like writing D and E. It takes a lot less time to write. And on the scanned lecture notes, I'm actually writing what I'm saying, but like switching back and forth here, it seems a little silly when most of it's written down. So part A, it equals 0. Part B equal 2. Part C, it doesn't exist. If we look at the limit as x approaches 3 from the minus side, x equals 3 is right here. And it looks like it's approaching y equals 3. From the left side, it's approaching 3. From the right side, it's also approaching 3. So at for x equals 3, we could actually say the limit does exist. That we only on part D, we only showed the minus side, but the idea there is if we did the plus side, we could show they're the same. Yeah,
Christine, why does it not exist?
because the first two are not the same.
Okay.
So notice we actually have a value at 1. X equals 1 does exist for this function. This line is not a continuous line though. And you can't, when you draw this line, if you're using a pencil, you have to lift up your pen to draw this line. You have to lift it up here to put a point here, and then you got to lift it up again to start drawing along this. So if you have to lift your pen to draw the graph, it's discontinuous. F of 1 actually exists, but with this, the limit does not exist. Because the limit is only about what's happening as we approach the graph from the left and right. That's pretty important. They have to be the same from the left and right. Does that make sense? So even though f of 1 exists, the limit does not. If we do the limit as x approaches 0 from the right, we're following this graph right here towards 0, x equals 0. It's getting closer and closer to 2. So the limit as x approaches 0 from the right is 2. We don't have a graph to the left. So there's only one direction this limit exists on. The overall limit doesn't exist. For x is 0, there's no limit because it's a one, the graph ends there. Yeah.
So for D, would it not exist too because it stops, so it doesn't approach from the right?
D, it does approach from the, oh shit, you're right. Fuck, I was looking at this point right here. That is not 0.3, this is 3. Way to go, Dave. I said that equaled 3. You're right, that's D and E. As it's approaching it from the left, it equals 4. As it's approaching it from the right, it doesn't exist. Thank you. I didn't fuck that up.
So D is D and E.
D is D and E also.
Yeah, but they
It
got
was
yes,
from
from the left,
like, asking from like, if it was.
But it has to be, oh, you're right.
asking for the left side.
Yeah, it's just asking from the left.
So it'd be 4. right?
It's 4. I wrote 3 earlier, but I said 3 earlier. It's 4. From the left side, it's 4. The overall limit at x equals 3 does not exist. The same thing for at x equals 0. The limit is 2 from the right side, but the overall limit doesn't exist.
And then the limit as x equals, or as x gets closer to 1 doesn't exist either because the top 2 are different values.
Yes, because they don't lead to the same value. The only time you're gonna really have a graph that has a hole in it where the limit exists, if it is just like that. I can technically draw this without lifting my pencil. So even though there's a hole, this is like what we had with the last one, x minus 2 over x squared minus 4. For that part, I was able to draw the line. I could draw a circle there and then keep going, and my pen doesn't lift up. There's a hole at x equals 2, but the limit actually existed there. I'm not showing what I'm talking about. Switch over. So if you could draw the whole picture, even the circle, and then keep going without lifting your pen, then you have a limit. We couldn't do that here. I do this here, I can draw the circle, but then to keep going, I gotta lift up my pen, and I gotta lift up my pen again to draw the graph. This, even though we have a limit, this line is not continuous. We'll talk about continuous and continuity later. This is actually discontinuous here. We'll talk about continuity, I think it's next Thursday. We do have a couple more ideas here. One more idea for 1.1. Infinite limits. We can have values on the graph that when we approach a specific x value, the y value is infinite. These occur at asymptotes. I'm not going to do example number 5. The idea on example number 5 is you just change all the pluses to minuses. And you do as x approaches a from either side still. I'll show you graphically examples of both. So if the limit is x approaches a from the left and the limit is x approaches a from the right, both equal positive infinity, we say that the limit is infinity. When it says increases without bound, it means there's no boundary to how far it can go up. There is no limit to how far it can go up. It can rise forever and ever and ever. I think the expression is less helpful than looking at examples. So we're gonna look at the example of 1/x - 2 from the left and the right. I'm gonna shift over to the camera real quick. We are gonna look at the limit as x approaches 2 from the right of 1/x - 2. And we will look at it as it approaches it from the left for 1/x - 2. And then we're gonna do the same thing for x approaches 2, not from left to right, of 1/x - 2 squared. The graph of 1/x - 2 has an asymptote at x equals 2. And on the left side, it does this. And on the right side, it does that. This is 1/x - 2. So as we're approaching it from the right, this actually goes up to positive infinity. And as we approach it from the left, it's going down to negative infinity. So these are different values. We would say the limit as x approaches 2 of 1/x - 2 does not exist. Oh, we're doing continuity on Tuesday. My bad. I forgot I skipped 1.4. We're gonna do 1.4 at the very end of class because I'm not testing you on it. And I really think if I teach it right now, most of you are gonna be like, nope, fuck this class. And you'll drop, and you don't need to. It's not, you don't really need it for the entire rest of the semester. 1.4 is actually shows you how to do a lot of the proofs. It's called the delta epsilon proof. I'll show it to you later just so you've seen it. You won't ever use it until you get to like real analysis or something like that if you're a math major. If I look at 1/x - 2 squared, well, as I approach 2 from the left, I still have an asymptote there. I can't plug it in. But like, if I do 1.99 - 2 squared, coming from the left, it's actually still a positive number. So for this one, the graph goes up to positive infinity from both sides. So here, the limit as x approaches 2 from the left and from the right, both equal the same value, infinity. We say this is infinity. When I say same value, infinity is not a value. It is not a number. It is a concept. All right, that's it for 1.1. Let me take roll real quick. And I'll just mark off the names I see online real quick. Michael. And if someone missed today, but they still did introduce yourself. It's all good. They've been using this. This is annoying as hell. I'll show you the way this looks real quick. I'm gonna just flash this so no one can see anyone's like ID number real quick. The roster has got one full page. It's got 3 names. That's it for the second page. And the third page has more fucking names. Like, could you not have made it so that it fits right when you print it? All right, let's go through the list. If I fuck up your name, please say something right away. Don't let me be the asshole that says your name wrong for 15 weeks before you go, hey, Mr. Jones, you've been saying my name wrong. Don't make me the asshole, because that really you'll be the asshole for not telling me I said it wrong. Don't be an asshole and make me look like an asshole. Correct me. Roberto. Yeah, okay. Alexis.
Alex is fine.
Alex.
Yeah.
Estefania. I hope I said that right. Andrade Meza. Well, we'll see if they said something on. Gregorio, you said someone you walked up. Cecilia?
Here.
Hi, Cecilia. Ashton?
Here.
Your fucking last name is awesome. Matthew?
Here.
Hey, Matthew. Jose?
Here.
Jose Cabrera. All right. Jose Del Toro. JJ, got it. Thank you for helping me the other day. Dalton. Hey, Dalton. Cody. Oh, he came in. Nice. I saw you hop on Zoom hella early just to make sure it kind of worked.
Yeah.
Lizette. Preston.
Here.
Edgar.
Here.
Hey, Edgar. Esteban.
Here.
Okay, you're gonna have to correct me. Cohen,
Yeah, that's what it's like.
did I say it right? Wow. Ansley, Ainsley. I don't know how to write that fucking phonetically. Like pain, like Painsley, but Ainsley, right? All right, I can remember that. There's 2 Carlos I see at least, so Carlos Lopez Chavez.
Right here.
Let's go with Carlos, Mija. Carlos. I can't say some fucking, I just can't do it. No matter how I try to get me to roll an R, you're fucked. If your name has a rolled R in it, sorry, I'm not doing it. Can't. I've tried. Cynthia. Osvaldo. Did I say it right? Isaac.
Here.
Isaac Perez.
Here.
Okay. Madeline. Jordan. Denise. Jer. Is that right?
Oh, it's Jair.
Jair. Jair. You wouldn't let me fucking say it wrong. Don't do that shit. Correct us. No, don't. No one wants to hear their name fucked up. Like if you say David, I'm gonna get it. That's fine. It's technically David. I don't care. Some people really care. Very rarely is my name fucked up. Oh, there's my other Isaac, Reynosa. I thought you answered to Perez. Ah, okay. I know Senzi. Vivian. Balraj? Did I say it right? Fuck yeah. Justin's online. Yeah, that's totally a fucking snob. There's even spaces in it. He doesn't have spaces on on his name on Zoom, but it's Van space Der space Meiden. So that totally looks like an elitist family, like, or the Vanderkamps or some shit like that. Christina? Venegas? James Wilkinson? Good morning, James. Eric? Zacharias. Okay, the one in the back. Ah, fuck. Ziri? Did I say it right? Say it again?
Siri?
At Siri?
Yeah.
So it's like a C sound. Siri. Or like iPhone Siri, right? Kind of sounds like that at Siri. Okay. And I think that's all of them. If you need to add code, we'll do it after class. Let's hit 1.2. 1.2 goes really, really quick. First off, you got a bunch of formulas to write down. And then I will. This is just how do we compute ones fast? If we have a specific thing, how do we find the answer fast? So if on like A, if f of x equals k, where k is just some number, that's what it means there. K is a constant number, then the limit is just that number. If the function is just x, then the limit as x approaches a is just a. The limit of, if you do 1 over x, as you approach 0 from the left, it's negative infinity. And if you approach it from the right, it's positive infinity. Now, we're going to have two different limits. We're going to do the limit as x approaches c, so the same value of f of x and then g of x. We're going to say the limit as x approaches c of f of x is L. And we're going to say the limit as x approaches c of g of x is M. As you're writing down the sum rule, I'm going to switch over to the camera real quick because there's a step missing here that's pretty handy. So the sum rule shows that this equals L plus M. But what it skips is it doesn't show that you can distribute the limit. We can distribute the limit. And before I switch back to show the other thing, there's a handy way to remember all of this. Every single rule. The left side is the limit of the sums. And the right side is the sum of the limits. So you can take the limit of the sums and that has to equal the sum of the limits. When did you go to bed, Cindy? Look so fucking tired. Why?
I was catching up on homework. I worked today, so I don't have time.
You had that much homework already?
Yeah.
Oh, that's fucked. Yeah. Okay, so the other rules, I'll bring them back up. We have one for difference. Difference is the outcome of subtraction. And this has the same thing. The limit of the difference is the difference of the limits. Three and four kind of go together. They're both products. In three, though, one of them is just a constant value. So in three, if we have like k times f of x, we can kind of factor out the k, pull the k outside the limit. If we actually have the product of two different functions and we're doing the limit, whatever the limits of each of them are, we can just multiply those. So the limit of the products is the product of the limits. You do the quotient rule, you're dividing. We've got f of x divided by g of x. Well, f of x's limit was L and g of x's limit was M. So we can just do the outcome as L divided by M. We do have the caveat that M can't equal 0. What happened? Yeah. The power rule, if we have f of x to some n power, we can actually just move the limit inside. I'm going to show 6 and 7 on paper real quick, because those are a little harder to see. So 6, we had limit as x approaches c of f of x to the n power. What we're doing is we're moving that limit as x approaches c inside the brackets. And this value equals L, so this becomes L to the n. That's called the power rule. And then the root rule has something similar. The limit as x approaches c of the nth root of f of x. When I draw a radical sign, I bring a tail down to show where the radical ends. I think it's easier to read. I can move the limit inside. This value is L, so this is the nth root of L. Or L to the 1 over n. These are called the limit laws. And I'm going to kind of show you how we do them with an example. How these are used. So that's the example we're going to do. Did anyone need the page back up with all the equations? Okay, let me put it back up. Ainsley, I sure hope you like my teaching, because I know you have me for another class too. I won't fuck up your name in that class. How about that? Everyone ready? All right, so let's take a look at working this one out. The idea here is I could treat this as like an f of x, and this is a g of x, and this is like an h of x kind of thing, which means I can break this up. We had that sum and difference rule. I can break this up into these. That's a square. If we look at the limit as x approaches 4 of x squared, we could do it from the left and the right, and you're going to see that this equals actually the value at 4 squared, which is 16. Here, I could actually break this down a step further. 2 is a constant times x. I could put the 2 outside. Like that. This is like the one that had the rule with the k. So whatever k was, that was just the value there. And the limit as x approaches 4 of x, this was I think our second rule. It's just 4. So this is minus 2 times 4 plus 4. So we have 16 minus 8 plus 4 is 12. Everyone ready for a little bit more? Okay. So if our function is a polynomial, or any polynomial, and we tend to call polynomials p of x. If p of x equals c0, which is a number that's like our k, plus c1 times x, plus c2 times x squared, plus c3 times x cubed, plus dot, 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 plus cn x to the n, where our c sub I values, these are all just coefficients. These are numbers. If A is a real number, the limit as x approaches A of P of x equals P evaluated A. The real thing, the real way to identify a polynomial is there are no negative exponents. They're all just positive integers. You don't want fractions either. No negative exponents, no fractions. No fractional exponents, I should say. The coefficients can be fractions. But if we have a fractional exponent like 1/2, that's like taking the square root of x, and we can't do that for negative numbers. So we want to do just positive integers. So if we do the limit as x approaches 1 of x cubed minus 5x plus 6 to the 7th power. I can just plug in, these are all polynomials. This is a polynomial, and I could move the limit inside. That was one of the first things one of our first rules that we showed. I can move the limit inside. And now this is a polynomial. So I can evaluate it. I've got 1 cubed minus 5 plus 6 to the 7th power. This is 2 to the 7th power. Which is 128. I have some more examples, but we ran out of time. I will make a video for them and put it up this weekend. I do want to show to you guys real quick. If you look at the stuff in Canvas, at the bottom of each section, I have homework problems listed. So these are the recommended problems to go tackle. 1.1, if I scroll up, 1.1 had it also. So if you look at the bottom of each section, there are the example problems in there. I will see you guys on Tuesday. Godspeed. Yeah.